Okay, so so last time we started talking about this idea of the mean parameter space, or the set of realizable means. So let me go back maybe a little bit. So we had this canonical exponential family, and the idea is that there is a mean parameter, which is an alternative way of parameterizing. That's the model. Canonical or natural parameter, which is the expectation of P of X, which gives me a new set of parameters. And for every k hat, I get a corresponding mu. And from the differential identities that we saw, this is going to be the gradient of the partition function. So the easy way to see why this is useful is to note that if I have an IA sample, I can easily estimate these parameters by the sample mean, which is going to be unbiased for this. But estimating k in general is harder. So that's the main advantage. And then there's this deep result that we can invert this map in general. So so there's this speaking of the gradient, so this is in the normal family. This gradient maps the set of natural parameters to the set of possible mean parameters. And in general, this set would be a subset of all possible mean vectors that you can realize by a distribution that has densities on X. So if I put a distribution on X, then that distribution induces a distribution T of X. So I put a distribution on X. T of X is fixed. That would induce some distribution on T of X. Under that distribution, this T of X has a certain mean. And as I vary the distribution on X, the distribution T of X varies and the mean of that distribution varies. And it traces a set, in this case R2. And so that set, what we call that set is this M. Let's call it, for example, the set of realizable mean parameters by any distribution that has density, some density, with respect to the underlying measure. So if the underlying measure is Lebesgue, then this is just basically the all continuous variables or the continuous distribution. So then obviously the integral as it varies density, this takes different values, and as it varies in all densities, this takes the carves out the entire M. So there are some interesting ideas here which we can skip. So the idea is that maybe just point out, because this is very cool, but just very briefly, that this is really the convex hall of the support of the push forward of this measure under this map T. So there's this underlying measure, and so then, for example, in our case, let's say very quickly what that is. I have T of X, which is X squared. And in one of the previous lectures, I talked about push forward, if anyone remembers, push forward of a measure. Okay, zero recollection. Maybe I misremember, maybe I didn't talk about it. But I think if we talked about it, I don't know what in what context, but in this course, somewhere, that if I put a measure on a space and I have a map, then it pushes the map, the measure onto the new space. Okay. What context do we talk about this? Sorry? Yeah, maybe in that, yeah. You know exactly completeness. Oh, right. Maybe, okay, right. So that, good, great. So you have good memory. It's actually here, right? It's here. Or yeah, okay. So the simplification. So the idea was that if it's actually the same context that we talked about. So I was trying to like sketch the idea how you prove completeness in a full rank family, and the idea was that if you start from this density family is this, then I can simplify the parameterization. That was another platform. So I'm going to simplify this parameter. Then I can also simplify this to just the identity mapping. So the way I do it is by pushing forward mu to this map P of X. Then, so that's this thing. Push forward the mu with respect to T. So it pushes the measure on space X onto a measure in RD. And that with respect to this new measure, T will have the same. So if you recall, this is like a theoretical device that's useful. So this push forward is in general not going to be a measure that you're familiar with. So for example, so this is sort of, people recall this, maybe as a side note. Okay, so that's the setting. So this measure in our case would be, suppose I have, so I have T of X and nu is the big measure on R. So what would happen here is I have the big measure on the real line, and then I push it via this T to R2. So what do you think the push forward of this measure would be? So if you think about this, it has to, any point here would live on this parametric curve. So the support of that measure, the push forward. So nu push forward by T. How did I write it? Okay, yeah, nu push forward by T, or we can say nu OT minus 1. These are the same notation. So the support of this will be that, because and zero everywhere else, but it's here, and sort of uniform on this, if you imagine, because this is uniform on the real line, so you put the mass uniformly on this. So that's the push forward measure. So the distribution that puts mass. So you can see it doesn't have, for example, densities respect to the two-dimensional Lebesgue measure, but it's a perfectly fine measure. So if I want to, for example, compute what is the measure of the set, it's just a mass that's on this part of the curve. Okay. If I like want to like what is the measure of the union, it's just this mass plus that mass and so on. It's a little bit tricky to work with, but it's sort of intuitively it's clear. So what happens if I put let's say if I have a certain density here, if I put a density there, so the expectation. So imagine, okay, imagine I put a distribution on X that has two values. So let's say X has, this is like, forget about the logic. If X has two values, let's say A1 and A2, with probability P1 minus P. Okay, so what would happen to the expectation of T of X? Just want to give you some intuition what this is about. T is this. So what will be the expectation? Okay, but that doesn't help much. But this is good. It's easier to actually calculate this directly. Right, this works, but so X takes two values, so T of X takes two values. if X takes value A1, so it's this. Okay, so it's like P A1, A2 plus 1 minus P. A2, A2 squared. So A1 is somewhere here, and A2, A1. So let's say this is TA1. So this is A1, this is A1 squared. Okay, and let's say this is A2, then this would be, let's say this is A2. Say this is A2, this is TA2, this point. Okay, what is this? This is the mean of that distribution. So where does this mu land? This is a convex combination. So it would be like somewhere in the line segment. Okay, and as I vary P, this is gonna vary in this region. Okay. So now let's say X takes 3 values, right? Takes A1, A2, A3, would probably be P1, P2, P3. They sum to 1. So what would be the expectation? So it would be P1 times, so in general, it would be like summation Pi, Tai, right? Like from 1 to, in this case, 3, but let's say this is now A3, this is 3, 3, right? So P1 and P2 can be anything between 0 and 1, and then P3 is 1 minus. So as I vary, so what would be this, what this quantity is? This is again a convex combination. Anyone can imagine. So you'd form the triangle, it's going to be somewhere in between. Okay. And so as I vary that distribution, it's going to carve out everything in this triangle. So you get everything here as I vary. Okay. So if I add another point, it's going to be like, this is the convex hull of the 3 points. What is the convex hull? The smallest convex set that contains the point. So, or another way of saying it is to set up all convex combinations of points. Okay, so if I have 3 points, the smallest convex set that contains all of them is just this triangle. Or it's the set of all convex combinations. So anything in between is a convex combination, anything outside is not. Okay. And so this really, the mean is going to be the convex combination of TRA1, TRA2, TRA3. So this is really the convex hull. So this belongs to the convex hull. Hull of TA1, TA2, TA3. And as I vary P, let's say A1 and as I vary these probabilities, I carve out all the points in the convex hull. So it would be putting different masses here, and then it pulls it towards one of these or like in the middle. So you can imagine the mean would be like a convex combination in between. Well, okay. So if you haven't seen this, this is a very geometric, interesting idea. Okay. Sounds good? Yes. So it would be somewhere in that line. Because this is a linear, like it's a linear combination with coefficients that add to 1, it's going to be in the line. So the convex hull of, so this belongs to the convex hull TA1 and TA2. The definition of convex hull is the smallest convex set that contains, the convex hull of a set is the smallest convex set that contains those points in the set. The smallest convex set containing a set is the convex hull.
The smallest convex
set, yes.
Containing
a set. So convex hull of, so convex hull of S is the smallest convex set containing S, or it's equivalently the set of all sort of all convex combinations of points in S. So you take finitely many points from S, you form a convex combination. Another sort of finite set of points, convex combination. Convex combination is like a linear combination of coefficients that add up to one and they're not. Okay. Sounds good. At least roughly it should be good. So this is a very interesting concept in convex analysis. And so it's like you have a set of points that are not convex. So if I give you 2 points, this set is not convex. How can I make it convex? I have to add everything in between to the set, but that's enough. I don't need more. Once I add everything on this line, then by definition, convex is going to be convex. So imagine this definition. You can see I have to add all of these linear like convex combinations because that's required, and then that's it. So intuitively, like you know what convex combinations are. Like sorry, convex halves are. Right, the convex half of these two is this line. The convex half of this three is that. Okay, so now if I add another point here, 4, then I would have another point. I would get the convex half of those 4 points. And then if you can imagine that, if you can spread the mass continuously everywhere, then I have like a mass. So this is like saying I have mass P1 here, like a point mass here, P2 here, and P3 here. Then the convex hull. If I spread out the mass everywhere here, I get the convex hull of all the points. Okay, I'm gonna have basically the convex hull of that curve. So that's the set of all realizable. The epigraph, yes. In this case, it's not. It turns out to be the epigraph, but in general, it's the convex hull. Right. So you get the convex hull. So that's what I tried to say. So this is the support. So this is that set S, and the convex hull of this set S is the set of realizable. Because the mass is going to be spread around on this, and so you need to add all the like pairwise. So if I want to like look at this, I have to add all of these lines basically. And once I add all these lines, then okay. So you can imagine like take more points, and then you can see gradually like covering this whole thing. So this short thing here, sort of the same as for the period. The set of realizable mean for the boundary is the convex hull is for the push forward measured by T. So it's a very geometric, interesting sort of object. Okay, so the push forward of the Lebesgue measure by this map is a distribution like sort of uniform. This is the support is really this is support we care about. And if you take the convex hull of the support, you get the geometric shape, which is the set of realizable. The whole point of that theorem that I want to talk about is that everything in that convex hull is achievable by by the exponential family that has this condition. This is the non-trivial part. Okay, so this can be anything in the convex hull can be achieved by some distribution of mass here. The idea is that the exponential distribution that we put on is enough to achieve every point here. Okay, it's a pretty tricky concept. Yes. Yes, basically you just need two. Let's say A1 and A2, P1 and P2 with that. So I have to have everything here. If I change A1 and A2, this is a bit different distributions. So I have like a point distribution that's supported on these with some probabilities I can carve out. The issue is that none of these distributions I'm talking about has density with respect to nu. Okay, so you have I'm doing the discrete case so that you understand. But I actually have to spread the mass continuously because none of these distributions that I'm talking about are included in the definition of image because this doesn't have density. But you can imagine, once you imagine this setting, if I have a continuous spread of the mass, then it's just kind of like give me one, so like it's like a approximation of a sum by an integral. So you give me some point here. If I change that distribution of mass here, it gives me something here. So that's like in the limit you can imagine that would happen. But the key is this set can be, so anything in the between can be achieved by some distribution of the mass. The thing is that that exponential form is enough. So if I spread it like e to the negative theta t x, or e to the basic, and in this level, the density would be like e to the theta t, because it pushed forward, it would be like, as long as I do spread like this, theta t minus a theta, this kind of spread of the mass is enough to achieve everything in between. I don't have like within me the like mass. For different theta, this gives me different spread of the mass. That's sort of the intuition. Yes.
Does that mean you don't have to achieve this? Like anything that's specific that's square can achieve this problem.
So I can fix this. Then I fix the measure. Then if you look at all possible densities, so using my density tab, if you push it through this, then basically you see that the mean of those distributions would be you could achieve like all possible points here by those distributions, all possible densities. You don't have to, for example, have a Gaussian. Yes, you don't need it. But the thing is that the Gaussian is enough to achieve every point here. So that's the thing. Okay. So you just need to worry about Gaussian if you want to achieve every point. It could be possible that if I go to the exponential product, maybe I just cover this hash. Okay, it's not possible to achieve. There is like a certain part of the space that they can achieve by exponential distributions, but this other part I need to go outside the family. So that is all the same. No, you don't have to worry about it. You cover everything in between. Okay.
But when you say is the Lebesgue measure,
Nu is the Lebesgue measure. That's the underlying measure which is circulation taking place.
yeah. So that means X is uniform.
No, so the Lebesgue measure is not called. It's uniform on R, but it's not called. It's the notion of uniform distribution mass over infinite real life. When you push it through this, it's not a measure. But let's say when I put like a distribution of X, I actually put a density distribution here. So the resulting distribution we call distribution. So then I say, for example, this is not that. So for example, I could say, can I say? So imagine I have the same setting, but I set P of X to be e to the negative x positive. Okay, so this is a density. This is like exponential density, right? With a certain rate. Right. I couple this with nu, then this gives me a distribution on x. So x would be exponential 1. Okay. Under this distribution, I would have a certain mean, right? So that would be like, for example, the push forward under this distribution would be like the mass would be like here. Because I have the Lebesgue measure, but then I put a distribution on this, on the real line. It's like we are distributing mass on this part of the line. Okay, and then you'd get something like that. Okay. And the mean of this would be somewhere, it's actually tricky. What would be the convex hull of the support here? So it would be everything. Okay, then this is not good. So this for this particular one is a particular distribution, and then you get a point here. This is confusing because this is just one density. One density you put it, and then the mean would be somewhere. Let's not worry about this. It's going to be confusing. I hope like there's some part of this. So for example, if I change this measure, this picture will change. If I, for example, let's say this you can think of the usual exponential random variable, let's say, is exponential family like this. If I allow all the lambdas, so this you can think of as really really the exponential family associated with t of x. It's actually not two-dimensional. Yeah. So if I, for example, yeah, that's not going to work. So I have to do yeah, it's going to be tricky. Yeah, it's going to be more confusing, unfortunately, if I do this. There's a problem, like like the exponential random graphs, which is easier because it's discrete. Basically, the underlying measure is discrete, is much easier. So maybe also that doesn't work out. With this version, this is the measure actually density. I can't put a measure x on so I can't put the measure x on. So the measure u on x. I put x. So this plus the density. So if you see the definition, this is the expectation under the distribution of density p with respect to u. So once you do this, as you vary this p, this u recovers itself. Okay. Any questions? So we fix the measure u. We consider all possible densities like this, that the probability is. Okay. So this defines the set of all possible probability distributions that have density respect to u. I can put them on x, I can't do anything u. Now we get the set of all possible. Okay. Sounds good, yes.
Why do we need to do the main parameterization? I mean, can we talk about like the set of all possible values?
It's related to, so what do you mean the set of all mean
So
parameters?
if you were saying that we have a distribution that can or that could produce like means of or any mean, but do we have to use? Because we first talked about main parameterization to be able to talk about this, but I feel like
No, you can define this, but let's say if this density, the set of density varies in the exponential family that we talked about, that would give you the set of mean parameters for the exponential family. Okay. So we're talking about exponential families. So, and these parameters are meaningful for the exponential family. So here is an example of density. So we have this density respecting u. We get a set of means. What I'm trying to say is that the set of means is all possible means. I mean, that's
we don't have to reparameterize this.
no. Reparameterization. I'm not reparameterizing. This is another parameter. But reparameterization means that basically this map. Let's say this map is invertible. There's really no distinction between theta and left. So that's reparameterization. You don't have to worry about reparameterization. Okay. Yeah. So if reparameterization is what you're stuck on, forget about that word. Okay. We're talking about reparameterization. Okay. So let's just restate it here. I'm not going to talk about the proof. It's just saying that the result says if you have a full rank for exponential canonical exponential family, then if A is essentially a smooth, which is, let's say if the that's a technical condition. If the interior of omega is the entire omega, let's say there's no boundary. Let's say omega is open, then you don't have to worry about it. The parameter space is, oh, this is only matter if there's a boundary. Then under these assumptions, the gradient of A is a one-to-one and onto mapping from the interior of omega to the interior of the set of realizable. So anything that can be achieved by density can be achieved by an exponential family. And the proof of the one-to-one aspect is related to that covariance being the Hessian. So this part is sort of easy. Maybe I'm not going to repeat that. The tricky part is this part that this is onto. For the onto part, you have to be able to show that basically this gradient mapping, if I try to solve this for any mu reason that is in the interior of M, then I can find it. Because the candidate here is this gradient of A is going to be the mean. Okay, so I want to say that if it's possible to achieve a certain mu with exponential family, the gradient of A at figure has to be equal to mu. So really what this theorem is saying that I can solve this. This equation is solvable if mu is in the interior of the domain. Sorry, in the interior of M. And let's agree, like accept that. Let's skip the proof. So why that matters? Because if you go back, so this we did before, the significance for statistical inference, if you have IID samples from the distribution, which is again this Gaussian exponential family in canonical form, you write down the likelihood based on this is another exponential family with the same dimension, but now there's a potential here. You get 10 times that. We try to calculate the LME. We take a log, differentiate, but it's a log likelihood, and then differentiate. And the end result is that you have to say gradient of the equal to omega. This we did before, and then you have this. When you try to solve the energy, you have to solve it. You can solve this if this is in the interior of the set of realization. That theorem allows you to say that this inverse, I can invert this now. The MLE for parameter theta exists if it's in the interior. Okay. Sounds good. So up to this point, we have done that before. If you rename some parameters, if you rename this to 10 times in your hat, then it comes out as you see if it's minimizing this. You take a gradient, you get mu hat minus gradient of equal to 0, which is this. So we did this in one of the previous lectures early on. It might not be possible to solve this, but you can solve this if this is convenient. So for example, in the Gaussian case, this is going to be always possible. This is going to be like xi and xi squared, and so whatever you do, it's going to satisfy that inequality for the variance. And so this is always going to be okay. So nothing wrong. In some cases, you might end up with something which is at the boundary. So the existence of the MLE in the exponential paradigm is related to that deep fact. Okay. Yes.
That makes sense, but isn't this result also just like a direct consequence of like certain convexity conditions that seem right, like existence of like a maximum like if the Hessian is positive definite, then
If things are strictly convex, there's no reason that a minimizer exists. So can you give me an example of a strictly convex function that doesn't have a minimizer? There exists such thing.
This is a line.
No, no. That's not, line is not strictly convex. It's both convex and concave, but it's not strictly convex. So can you give me an example of a strictly convex function that's doesn't achieve its minimum?
Oh, sure, like, yeah, the L1 regularizer.
No, L1 regularizer is fine. This has a minimum. We want, like, this is a strictly, it's not a strictly convex, and it has a unique minimum. That's like, so I want something which is strictly, this is not a strictly convex, but achieves its minimum, that's fine. I want something which is strictly convex, but doesn't achieve its minimum.
It's like convex, but then at the minimum, it's like a straight line.
This is not a strictly convex. Because of the flat part.
That's all.
This is convex.
No, it's quasi. It's like it doesn't have a, like, what's it?
The way that I wrote it is like convex. You could have quasi-convex functions, but this one is going to be convex. Fine. You can have convex functions that have flat parts. So, for example, this is a convex function. It's not a strictly convex because it's flat. Right? It's close. So what do you want? The example that you can give me is this thing. So f of x is e to the x. So this function is convex, and it's also strictly convex, but does not achieve its minimum. Goes to infinity. So those things could happen. Although things are smooth, and let's say your chloride is strictly convex, something like this. So things are trickier than they seem. Okay. So if you're interested, go read the proof. So a lot of this is trying to show that there exists. The function which is convex is essentially smooth, strictly convex, depends its unique minimum at some point in the interior zone. So you need all these conditions. So it's not enough to be strictly convex. Strictly convexity implies uniqueness. But you need these two properties to force you to have a minimum. Coercivity means if you go to the boundary, things blow up. This means if you go to infinity, things blow up. Essentially, it's smooth means if you go to the boundary, it clearly blows up. So if you have a function, so you want to prevent things that look like this. So if you have a boundary, you can have a convex function whose minimum occurs at the boundary. But if the function goes all the way to the boundary but just blows up here, so the derivative blows up, then it forces you to have a minimum inside. So this is essentially smooth. Coercivity like prevents this. So you want this to this business that I mentioned. So you want to what is the definition of coercivity? Anyone knows what coerce? Yeah, coerce. Coercive means so if you go to infinity, it goes to infinity. So that takes care of the infinity, the bound that so it's unbounded. But essentially, a smooth part takes care of the boundaries. There's something which is coercive, it can't happen at infinity. Essentially, a smooth can't happen at the boundary. The strictly convex has to have a unique minimum. So part of this result is trying to prove something like that. So you want to prove that these coercive strictly convex is true because and essentially smooth, then there's a unique minimum in the interior. Once there is a unique minimum, the gradient has to vanish. You prove that there exists a theta for which the gradient is zero. And the gradient of zero is the same as gradient equal to any u, because you can shift. By shifting, you can map everything back to zero. So basically, the idea is an interesting analysis. So you say if the general case is equivalent to, so this is like the high-level idea. The general case is equivalent to if I assume that zero is in the interior and the set is zero. This problem. And I'll show that in that problem, there is a unique minimum in the interior. Because things are in the interior, the gradient has to vanish. So it is, this happens at that. So there exists a point. But it requires some work to get there. But you have the right idea. So strict convexity is needed, but it's not enough. You need a little bit more. Okay. If you're interested, go over the proof, and it requires some like convex analysis, some sort of interesting convex analysis. Any other questions? Okay, so the like punchline is existence of unity in the exponential family is tricky, but as long as this mu, which is this is the estimate of theta, if this is in the interior of that set of realizable means, then you're guaranteed in the full rank family to have that. So this is important, for example, in logistic regression. If you've seen, for example, logistic regression on separable data, there's no solution. So that's an example where things are violated. But we have talked about this a lot. And so maybe I'm gonna end with that last slide. So this is interesting. So all of it is interesting, but there's more. And not only the exponential family achieves any realizable mean, but it's the maximum entropy distribution that achieves that realizable. So among all possible distributions that have the same mean parameter, the corresponding exponential family is along the maximum entropy. For example, among all the random variables that have a certain mean and a certain variance, the Gaussian is the one that has the maximum entropy. Okay, this is a very interesting property. So anyone knows the entropy? What is this entropy? Shannon's kind of entropy. So what is it? H, yes. So let me do it for the discrete case because it's sort of easier to argue. So if I have a discrete distribution, so entropy is a property of a distribution. So a discrete distribution can be represented by a vector. So this is a distribution on let's say 1 to k. So a random variable that takes values 1 to k, so 1 to up to k, with probability p1, probability p2, k. Random variable that does this has a distribution like that. So let's work with the discrete case. So what is the entropy of this distribution? Pi log pi negative. So let's call this h of p. So this is p. Sometimes you say this is the entropy of the random variable. So what does it measure? It measures how uncertain things are. Okay, so a distribution that puts all the mass, let's say here, almost all the mass here, we have a lower. The one that distributes it uniformly has the maximum entropy. Okay, so without any constraints, the maximum entropy distribution is the uniform distribution. Okay, so if I just maximize, let's say argmax over all p, that like p being is a probability vector. It's a probability vector. So I'm thinking of like distribution on the set. A distribution on the set. So this you can think of it as the probability mass function. Okay. It's a probability mass function. So think of this as Pi is the probability that x is equal to I. I'm going to write P1 up to Pk, which is like that. So you can identify the set of probability distributions on K with a vector. And if I, let's say, minimize or maximize over the set, this entropy, the distribution that comes out is the uniform distribution. So without any assumption, the distribution has maximum entropy. So the entropy is the measurement segment. It's the smallest, so it's going to be 0 basically when all the masses are one, for example, or every one of them and the rest are zero, it's going to be maximized when it's uniform. So it's maximum uncertainty. So the idea is that without any constraint, that the uniform distribution is this. But if I put a constraint, for example, I assume, so that's like without any constraints. So, but let's say if I want to say argmax this, P is in this set, but I want to have, so let's say expectation of a certain T of X under P is mu. I want to set the mean of this distribution, mean of T of X under this distribution to mu. Okay. Under these constraints, the solution would be an exponential family. Okay. For example, let's say the very simple case, T of X is just X. Okay, so what this is saying, argmax H of P is in that P. And the condition is saying expectation under P of X is mu. So which is equivalent to saying summation Pi Xi. Is it Xi? No, summation Pi times I is mu. Okay, because X takes values I with probability I. Okay, so this is gonna be I times Pi is equal to mu. Okay, so this is the condition, and these are a bunch of other conditions. So this is going to be equivalent to this, and then Pi is bigger than or equal to 0, and the summation Pi I from 1 to k is 1. So you're maximizing basically HP under these constraints. Okay, so this is a convex problem. So argmax negative Pi log Pi I from 1 to k. So this is a convex problem, and this is convex, or this is concave actually. So the minimum, like if you minimize, so this is a concave problem between linear constraints, or in linear equality and equality constraints. So we can solve this rather as a convex optimization problem. And the way that we do it is you introduce a Lagrange multiplier associated with this. If you introduce a Lagrange multiplier, you can write down the solution as what it turns out to be is Pi is going to be, so good here. Yeah, it would end up being, well, what would it end up being? So for example, if I introduce, maybe do it quickly. So what I would do is, there's this Lagrangian, which is negative Pi log Pi from 1 to k, plus lambda times, I'm going to put this as a penalty in the objective. So dualize basically this constraint. Yes, so P and lambda, okay. And so if, let's say, ignore these constraints for now. So if I have a solution, then it has to minimize this for some lambda, and you take the gradient set it equal to 0. What do we get is, what do we get? So let's say partial with respect to Pj of LP lambda has to be 0. This gives me derivative of this, which is log Pj plus Pj times, so it will be something like that, right? And then I get plus log, sorry, lambda j Pj, right? Right, so this is gone, okay? So this has to be 0. So maybe can someone do the, so this has to be equal to 0. Can someone tell me what Pj is? would be, sorry. This is 0. Exponential what? Is that true? So I get log, right? Log pj is equal to, I move it on the end, so lambda j minus 1, okay? And then so pj would be e to the lambda j minus, so okay, so we need another thing because this is, so let's do, I'm gonna add a mu as well. I'm gonna add this guy in as well. Add that as well. Let's add that as well. So if I add this as well, there's going to be that and mu. If we can recover this. This is 0. This implies is there a mu? Oh no, sorry. This is okay. Nu. Yeah, nu is going to be confusing as well. So lambda 1, lambda 2. Okay. Lambda 1, lambda 2, lambda 1, lambda 2, lambda 2. So you get lambda 1 plus what? Lambda 2 equal to 0. So then what we get is plus lambda 1j plus lambda 2. Right? So lambda 1j plus lambda 2, and then pj would be e to the lambda j. Okay, 1. Yes, 1 is enough. So I get lambda 1j plus, or the e to the lambda 2 minus 1, right? And the way that, so this solution should look like this. So this is some constant. So really pj is c e lambda j. Okay, and then the constant is set so that it sums to 1 because you have to satisfy this constraint. Okay, if you remember the Lagrange, the way that you do it, you set the c. So c really is the normalizing constant. So you can see that pj is basically proportional to e lambda j. That's what you expect. So it's like p of x is proportional to e lambda x. So that's the exponential family associated with t of x being equal to x. Okay, so if you did it with general t of x, what would come out is p of x is proportional to e lambda t of x. Do it as an exercise. And, the proportionality is gonna make it, so it's lambda 1. You can call it whatever. So, but it's a parametric family that looks like this, which is the exponential family. So if you really solve the maximum entropy condition under the assumption, sorry, maximum entropy problem under the assumption that the point t of x I ti. So you have to solve this optimization problem, and the solution turns out to be something like this. Okay. So the exponential family finds the maximum entropy solution under these constraints.
Does this hold for multivariate continuous?
Sort of. That's what I'm waving my hand around. So the general idea is that true, but then you have to worry about like regularity conditions and stuff like that. But you can see like the gist of it is like this. In the continuous case, if you found a very nice result that proves it, I would be happy to hear about it. This is generally known. Okay, but under what conditions this problem has a solution? So you can see that just the existence of an exponential family for this is a little tricky. The fact that there exists an exponential family that achieves this for any years. But assuming that it exists this, then showing, this is the nice way to just start from mix optimization. So you have to do it in infinite dimensions. Version of that. You do it properly, then something like this should come out. Okay. Someone probably somewhere has done it properly. So. Yeah, the issues with this defining it is this. You have to assume things that happen in densities, and this would be like integral density. And then it's, but in any case, so this is good enough, I think, for our purpose. So exponential families achieve maximum entropy under the additional moment condition. So if you have, for example, you observe your data, from your data you calculate, for example, empirical moments. And you want to find the distribution that maximizes entropy subject to those constraints. Exponential families. Okay. It's another manifestation of the idea that they occupy a very optimal place in this case. Okay, so that's the last thing that I want to talk about. Any questions? Okay. I think we talked about enough about exponential families. Now let's move on to the next topic, which is going to be so this idea of Cramer-Rao, lower bound, or information inequality. So let me ask you guys, how many of you have heard about this? Cramer-Rao, probably heard about it. Okay. Yes, if you have taken, let's say, like an undergrad course, maybe. So this is a very famous classical result. And so we're back to those ideas that we started. The course with the decision theoretic framework. So exponential family was basically a detour into like a parametric family that has a lot of interesting properties. So back to the decision theory and back to the UMVU. Okay, if you recall still what the UMVU was, uniformly minimum variance of one estimator. So we did have a nice theory when there is a complete sufficient statistic. So if there is a complete sufficient statistic, then there exists a UMVU. And then there are basically approaches that we tried. But you saw, or like from the exercise or from the lecture, that it's often hard to find the UMVU. So obvious. So this Cramer-Rao lower bound gives you a lower bound, and the variance of the unbiased estimators that's easy to calculate. Okay. And sometimes, so you don't need the U. So if I have the UMVU, I can evaluate its variance. It's the minimum possible variance for the unbiased estimators. But if I don't have the UMVU, I still can get a lower bound. What is the best variance? So this to put some sort of it's like performance limit on like how much you can reduce the variance of an unbiased estimator in a parametric model. And so the idea is very simple, and it also plays like a role in asymptotics. So on. The idea is simple and is to use the Cauchy-Schwarz inequality, also known as the covariance inequality. So this is the Cauchy-Schwarz inequality with the random variables. And if you remember the L2 representation of random variables, in the product square, this is the norm square. Cauchy-Schwarz. And if you apply it to centered random variables, this is another form. So x and y are centered random variables. This side would be covariance. This would be variance. The product of variances. For this reason, it's called covariance inequality. So the plan to use this to drive a lower bound of the UMVU, or the variance of the UMVU, or the variance of the unbiased estimator, is to rewrite it. Okay, so I take an estimator delta, and I take another estimator, or potentially something even that's not an estimator, as psi, and so the covariance of these two squared divided by the variance of psi would be a lower bound on the variance of delta. So imagine dividing both sides by one of the variances. So I get a lower bound for the variance of delta and the variance of these two squared by variance. So what I want to do is So delta would be any unbiased system. And I want a lower bound that is not dependent on delta. So the way that we have it here is dependent on delta. But if you play your hand right and then pick psi properly, then you can get rid of this delta and you get a lower bound that falls for any delta. Okay, so that's the idea of the Taylor route. So we use the Cauchy-Schwarz inequality to drive a result that falls for any unbiased system. Is that idea clear? Right. So, okay. Questions about this? So let's see in the remaining time how much we can go, or how far we can go. So here's the result. Maybe I'll come back to that. So the result is something like that. So if delta is unbiased for g theta, this is like a precursor to the Kramer-Rao bound. This is called Hammersley-Chapman-Robbins inequality. So if I take a parameter theta, and another parameter that in the right is theta plus h. Magic theta is in RD, so addition is meaningful. So there's different parameters. But for 30 derivatives, so I get different distribution in the family. And if this is absolutely continuous with theta, then and delta is unbiased for g theta, then I have this lower. So the top is the difference of this g and those parameters. And this denominator is the expectation of the log likelihood. So L theta and H is really so assume that they have densities. So this has a density p theta plus h of x, and this has a density p theta of x. So this is really p theta plus h of x divided by p theta of x. Okay, so if I form the likelihood ratio between these two parameters, the likelihood ratio of basically the model with respect to these two parameters, that's kind of what happens. So you have density here, density here, and the likelihood ratio. That will be the L. And so you can see this doesn't depend on the delta anymore. So this is just a like pick theta plus h and theta. For any theta and theta h, this side will be in order. And the way it works is we take basically psi to be this likelihood ratio minus 1 in the Cauchy-Schwarz inequality. And what you end up showing is the expectation of psi under theta is 0. And the covariance of delta and psi ends up being that. So if I write the covariance inequality of Cauchy-Schwarz, I get something like this. Covariance of psi delta squared divided by variance of psi. So this would be g theta plus h minus g theta squared divided by, so the variance of psi is, because the mean is 0, the variance is just expectation of psi squared, which is just squared. So you get the bound. So the only thing that you need to do is to verify this covariance and this 0 assumption. So next time we come back and talk a little bit about that. And then the way that you get the Kramer-Rao, because these are any possible values of theta and h. So I fix theta, let's go to 0. And as a result, I can take the limit of this goes to 0 and this tends to the Kramer-Rao. Or you can do it more properly without taking the limit. But this gives me an equality for any h as I let h go to 0. This side converges to what is only dependent on theta. Sounds good. Okay, so this was quick. Next time we'll come back and do it a little bit more properly. And we'll talk about the Kramer run. Sounds good? Okay. Thank you, guys.